Okay, can people see that?
Yes, indeed.
Yep.
Cool. Okay, so hi everyone. Today we're going to talk about GLAM. Anthony and I will do a deep dive into the GLAM datasets, how they're generated, how they can be used, and what some challenges we faced were when we were building them. Our goal is to inform everyone about the datasets in case they might be of use to you or if you're just curious. Okay, so at a high level, GLAM datasets are generated from a set of scripts in the BigQuery ETL repo that spits out SQL queries. These queries are scheduled to run daily with Airflow after the main ping data for the day has finished processing. The datasets essentially contain aggregations per client, as well as overall clients for every probe that can be treated as either a histogram or a scalar. Right now it's happening for both desktop and Phoenix Firefox. I'll be mostly describing the desktop datasets. So this is a screenshot from the desktop DAG, but Phoenix is nearly identical, and Anthony will go over some of the key differences. Okay, so I always find it easy to describe the datasets by looking at the DAG here that's generated in Airflow. So there seems to be a lot going on, but you might be able to tell by the names. A bunch of the jobs or queries that run in the DAG are doing roughly the same thing, but for different data types. So histograms, scalars, booleans, etc. So when we group those together, they look more like this. So here the colored bubbles I circle correspond to the colored labels, and these are where the majority of the work is happening. There's also user counts and percentiles, which I didn't color, but you can see where those fit. We also have to the far left a table that keeps track of the latest 3 versions of Firefox per channel, which we use for filtering the data. And on the right, there's a couple of jobs for extracting the data. And yeah, so I'll start by talking about the client's daily aggregates in the red circle. So there's 2 output tables, client's daily histogram aggregates and client's daily scalar aggregates. And at a high level, they both have roughly the same schema. There's 1 row per client per submission date, aggregated across a few different dimensions, including what I mentioned here, OS, version, build ID, and channel. For desktop, there's like a slight variation for Phoenix for what this set is. And each row contains aggregations for all probes of the relevant type found through the probe info service. So the scalars table includes both regular and keyed scalars as well as booleans. And for each probe, we want to aggregate it in a few different ways. So for scalars, we look at min, max, average, count, and sum. And for booleans, we keep a count of trues and falses for each user. And then for histograms, they're aggregated at this stage by summing all the values for each key. So in this example, if a user had these 2 histograms for a single submission, this is what the output would look like once we merge them. Okay, so now going back to the image, I pretty much just described everything in the red bubble. And so I'm gonna go on to the blue bubble. So for clients aggregates, as you may have guessed by the names of the tables, the main difference is that they're aggregated without submission date. So they have essentially the same schema, but they're aggregated across, the same dimensions. The key thing to note here is that since there's no submission date, we keep running counts that are updated for each scalar and histogram. So for aggregations like min, max, sum, count, and so on, those are easy to add a new value and keep the running count. The only one that's slightly unique to update is average, since we recompute the average when new data comes in by doing like sum divided by count. Okay, so that's actually it for the blue part. The green part is where things start to get more interesting. So let's take a look. So at this point, we're preparing the data so it looks closer to what gets displayed in the GLAM UI. And there's a few different things we have to do. First, we add some aggregations that we've not been keeping so far. So far, we only keep aggregations for users for all the combinations of the dimensions I mentioned. But here we add aggregations over all build IDs and all operating systems if you don't want to look at specific ones. We then normalize a user's histogram so that all its values add up to 1. This is how a user gets represented only once for all of their submissions. And then once it's normalized, we can drop the client ID and sum the histogram values to get a single histogram over all users for a given set of dimensions. So far, to reduce the time and space used, the histogram does not keep keys with 0 or null values. So again, in order to make the data ready to be displayed or used directly, we look at what type the histogram is labeled as, whether it's exponential or linear and so on, and we generate the full set of buckets for that histogram, and we populate any empty buckets with 0. I also mentioned here in the slides that we apply the Dirichlet distribution to the histograms so that we can compute error bars more easily. I don't want to dive too deeply into this, but I've linked the proposal that was created by Saptarshi Guha, I think back in April before he left, on how we can add the error bars to the histograms. Since some of the data we aggregated is actually sampled, I haven't mentioned that yet, but at the time when we were working on this, we didn't prioritize doing this because the sampling we do is only for Windows release data, which is still really huge. So we expect the error to actually be still pretty small. But I think this is one of the places where we might need more thought or work in the future on how we want to handle this. But yeah, the link is there in the slides if you're interested in more detail. So with that, I just wanted to give a quick example to be more clear about what the normalization looks like. So on the left column, there are a couple of examples before normalization where the values are just the sums from a user's histogram, and the right is what, when they're normalized to 1. So what about scalars? How do we prepare those to be displayed? They're a little different. We want to show all the user contributions in one distribution. So we need to create buckets to tally the users for a given probe. So deciding what buckets to use was a little bit tricky. So I'll explain what we had initially, which was based off of the original telemetry dashboard. I'll explain kind of why it didn't work, what we have now, and why it's kind of still not that great. So originally we had a fixed set of linear buckets that we used for all probes. So for example, buckets would be a size of 10 or 100 and go up to 10,000 with fixed increments. This was pretty bad because a lot of probes tend to have most of their data in the first couple of buckets, and they would essentially have a bunch of empty buckets for the larger values. So this had a couple of issues, like first of all, it didn't visualize very well, and secondly, you can't really draw conclusions or insights from the data too easily. Okay, so we wanted the buckets generated to depend on the range of values that a probe can have. And we wanted the buckets to be exponential because a lot of the data has a long tail. That was the nature of a lot of the data. So now the way we do it is we dynamically generate the buckets for each probe by looking at the minimum and maximum value they take. Or they have, and creating an exponential set of buckets to fit that. So there's, again, a link here if you're curious about how that function generates the buckets. Generally, there didn't seem to be an issue with this approach when we looked at desktop probes, especially desktop probes that were rich with enough data points to have a relatively stable range. For the data, but kind of somewhat recently, Anthony was looking at Phoenix probes with a small but growing amount of data. And he noticed that the dynamically generated buckets would change drastically over time for a given probe. And this kind of made it difficult to compare over time the data. And it was particularly true for newer probes. So again, this is one of those places we might need to assess how serious the issue is and potentially rethink how we're doing the bucketing. Okay, so back to how we process the scalars to be displayed. So we have these buckets that we generate. We also, similar to histograms, need to add aggregations for all the build IDs and OSs. We then need to assign buckets for each client with their set of dimensions. So for scalars, we use the bucketing system I just described, but Booleans are kind of included in this computation. So for Booleans, we do something else that also might need some rethinking. So in order to merge, like I mentioned, true and false counts before, but we want to represent a user in one data point. So we create 3 buckets right now called always, sometimes, and never. So for example, if a user only has true for a probe, the bucket would be labeled as always, and so on. And I think this idea came from some initial user research from a long time ago that like I got insight from Chetnon and things like that. But I think we also recently got some feedback that having more diverse buckets in this case to show percentages or ratios of true and false could be better. And then finally, once each user and set of dimensions has their bucket assigned, the users per bucket can be tallied, and the generated histograms zeros can be filled in the same way that I described for histograms. Okay, so that was a good chunk of the meat of how the data sets are computed. I kind of went over the red, blue, and green bits. And I'll quickly go over the last 2 bits at the bottom, the percentiles and the user counts, and then also some thoughts on how we could use the data. Okay, so the percentile computations are pretty straightforward. For both scalars and histograms, we compute all those percentiles listed there. For scalars, this is of course done separately for every aggregation, like how we have min, max, and so on. We have different percentiles for those. For histograms, the percentiles are computed on the final histogram produced that includes all users. Oops. Oh, I have a missing slide there. Or it's labeled wrong. Okay, well, anyways, user counts. So in terms of user counts, there's at least a couple of different counts we keep. The job that you saw in the DAG generates a table called GLAM user counts with the user counts for every combination of those dimensions, OS, version, build, and so on. We also have a total users column in the client probe counts tables. This counts the number of users that have submitted data for each probe plus the set of dimensions. So that way you can kind of look at the ratio of like, okay, for this set of dimensions, there's this many users. And then for this probe, like what's the ratio of how many people submitted the probe to that? Okay. So I covered a lot of stuff here, but hopefully, like given how the data sets look and how they're generated and so on, it's interesting to consider how they might be relevant to you. So generally, I mean, given what the data sets look like, if you want to look at user counts or probes or for probes or aggregations for an arbitrary probe, the data sets can be useful. Specifically, I linked to a proposal here that Corey shared with me by Emily, using the, Corey suggested using the GLAM datasets to help with operational monitoring. So essentially, if we want to look at changes or regressions that happen from one build or one Firefox version or app version to the next, it helps to be able to quickly reference aggregations for a client by build or version. And potentially the GLAM tables could be joined with other tables containing more detailed client information. And then, you could do further analysis from there. So like one use case for, like, for example, the fission release is a good case where kind of this approach to operational monitoring could potentially be applied. Okay, so that's all I have. Anthony has more info about challenges and building the data sets and so on, but I'm gonna pause for a bit if anyone has thoughts or questions.
So if we have feature requests for like automated regression detection, whose ear do we put those in?
So if you specifically want to talk about like the operational monitoring stuff, it sounds like Emily's team kind of is working on that already. Like they have that proposal. But also I was just talking to Corey that we might coordinate there for like the GLAM data sets. It's a joint effort.
That is something that no one has outright complained at me for shutting down. But every time people notice that that Cerberus no longer works and is providing them that sort of warm, comforting level of, oh yeah, nothing has gone horribly wrong. People do comment that they miss that. So
yeah, I do think that should live in this new, like our platform engineering working group. I don't think we've agreed on like exactly what the staffing is for that yet, but you can at least put it in Mark's ear, and Mark will hold on to it. Yeah.
Well, since Mark was the one who actually turned it off
Yeah,
2 Decembers ago,
I'm already experiencing that like coldness of that comfort being ripped away. So, but it's good to, yes. Cool. Any other questions or thoughts? I feel like I'm gonna have to go and reread through those slides. There's a lot that you covered there.
Right. There was a lot of content. It was a little dense.
I have actually a clarification point, and it's kind of obscure, but I think it's kind of essential. So like the histogram bucketing stuff you were talking about, like I'm just like not completely clear on it. And I think the way I'm not completely clear might be similar to the way other people aren't clear on it. So like Firefox has its own histogram bucketing algorithm, right?
Yep.
How does that, so like, but you said that GLAM does its own too, and I'm wondering how do the two interface with each other? Could you go into more depth on that?
So there was 2 separate things. There's like the histogram bucketing for histograms. We use the same as Firefox. Like we have the same buckets that Firefox uses for histograms. For scalars, that's where we made up our own algorithm. So the reason we bucket scalars is so that we can display them in like an aggregated way.
Yeah, it's like everything, like all the scalars, by the time we render them, we have a huge distribution of them that are turned into a histogram. And it's that bucketing, that the choosing how to bucket that histogram that's been generated by a large distribution of scalars, that is where I think most of what Rena was talking about.
Yeah.
And that's the issue there, is that especially when there are fairly new probes or the data is not very dense, it might change over time. And because we're computing the buckets dynamically based on the range of the distribution available, if that changes, it makes it hard to show like a line graph over time of what those distributions look like. So that's kind of a place where we want to maybe get some data science help to figure out how best to handle that. We still don't know how extensive an issue that is. We're doing some research to see like how many scalars does this impact, and we, anecdotally seems that the more stable and the longer the data has been there for a scalar, the more it kind of like normalizes around, and you see less like hopping around of the buckets that we generate. But it may be an issue where you're looking at something where two builds ago the buckets were different, but that's not easy to indicate on the graph that you're looking at. Does that help answer your question?
Yeah, that's really helpful. Yeah, there's just a lot to unpack here.
Yeah.
One sort of really high level thought that occurs as a use case for these data sets is maybe we could use it to figure out what probes are hardly sending anything or almost never occur in the wild or don't appear in the wild. That could we could probably use that data to probably just delete a whole bunch of code from Firefox, basically.
Which, well, we already have a problem right now where we have identified a bunch of things that can be removed from Firefox, and people just don't.
People just don't.
Yeah.
Yeah. I wonder if it would be easier. This is probably shouldn't go on for this too long, but like it might be the sort of thing that's easier to do in bulk, right? We're just going to remove all this stuff. If you have any complaints, let us know within the next 2 weeks, as opposed to like pinging every single person who would be responsible for that probe.
If we knew, yeah, who those people were. This is a lovely opportunity for migration when we're moving from Firefox telemetry to Glean next year, where everyone who cares about probes will migrate the ones they care about, and anyone who doesn't care about them, they get left behind and can die. But I have a question as well, if that's all right. I've been noticing a lot of talk about more feature additions and some focused scrutiny on scalars and histograms. Firefox telemetry is going to be an ongoing concern for the foreseeable future. It's not going anywhere, but Glean is the future. So how are you balancing sort of working on this system that is not quite in keep the lights on mode, but almost is, versus ignoring all the complications of things like scalars and only fixing that problem in terms of counters and quantities in Glean?
I have a comment on that, and then like maybe Rob has some ideas, or Anthony too. I was gonna say that like I did mention that like the way Phoenix is implemented for GLAM is pretty much the same. Like most of the code is reused. So I was talking about histograms and scalars, but I forgot to mention that there is a mapping that we did between those and like GLAM data types. So and I don't remember the names offhand, but like for example, I think count or something like that, we would treat that as a scalar. And so whatever mappings we found, we used those so that we could do the Glean stuff and reuse how it's computed. Does that answer your question?
A little bit, yeah. And if there's anything that can be put in, that can be built into the metric types, sort of guarantees or metadata to make that sort of aggregation easier, then do let us know, because I mean, counts were designed to be aggregated easier than scalars. Yeah. So if you're doing the same thing to both of them, we have failed somehow, maybe. So we'll, yeah, I look forward to chats in the new year about that.
Cool.
That's maybe a good segue into Anthony talking more about Phoenix and the implementation challenges around it.
It'll be more about GLAM ETL and BigQuery ETL. I'll briefly touch on Phoenix, but it'll be kind of maybe the same material in a slightly different perspective. Let me share the slides. Don't quite want to go full screen on this, so you'll see the ugly URL bar at the top. But yeah, I'll be talking about GLAM ETL in BigQuery ETL. So here are the things I'm going to talk about. I'm going to be talking about building the data sets for Firefox Desktop and building the data sets for Firefox for Android. And while talking about these, it'll typically be about the challenges that we faced while doing this. So GLAM is a nice visualization layer over these data sets that we've built for it. But all of the percentiles and distributions and counts are built using BigQuery. All the data is stored in BigQuery, all the computation is done in BigQuery, and we export the data sets out so that it can be ingested by the GLAM website. So first I'll talk about building the data sets for Firefox Desktop. And I'll split this into three main parts. First is handling schema evolution of the main thing. The second is handling the sparse histogram buckets for visualization. And third is handling complex SQL queries. So how do we handle schema evolution in the main ping? We all know that the main ping is this gigantic JSON blob full of all the probes over all the history of telemetry. And once we add something in, it's pretty much impossible to take it out. It's a living, breathing document. And it's been much of ire this year when it suddenly jumped from 6,000 columns to over 9,000 columns. So we need some way to handle adding new probes and letting GLAM figure out what those are. So we do this by dynamically generating SQL. It's kind of as gross as you think, but this is the general process for it. We have the probe info service, and this is the source of truth for what exists in the main ping. We use it to generate schemas for the main ping, and we also use it to templatize a SQL query so that we can pull out the necessary probes from the main ping. This templating script generates a very large SQL file, so large that we have to split it up into multiple parts. And then we use the BigQuery CLI or the BigQuery API in Python to run this file. So there's some benefits of this. We're always up to date with the schemas because we're using the same source of truth. It allows us to embed metadata from the probe info service into the queries so that we can use it for various things. On the other hand, it requires us to use custom scripts to run and manage these queries. So it's a little outside of the scope of BigQuery ETL, but in the time that we've started writing queries for GLAM, there have been other examples of dynamic queries in BigQuery ETL, mostly because Glean is this generic framework for sending data to the pipeline, and we need generic ways of running SQL that run on the same types of data, but with different applications. So now I'll talk about sparse histogram buckets. And what do I mean by sparse histogram buckets? So when we send a ping to telemetry, we don't send every single bucket that is enumerated by a probe. We only send the buckets that have values. And if we aggregate these buckets in GLAM, at the end, we might not always have the full range of buckets. And so if we don't have the full range of buckets, we might have a weird looking distribution because, oh, the very edges of this distribution are missing and aren't actually processed. We need to have the full range so that we can visualize it in a consistent way. So first, we embed the metadata into the columns of the query. So we do this in the first step where we dynamically generate the SQL. And so now we can query the range for the histogram. So here is a query in Redash using the client's daily histogram aggregates, where you can see the first, last, and number of buckets for each metric. So we've simply taken the data that's in the probe info service and we've embedded it into the data set. And so this metadata allows us to do interesting things, like generating bucket ranges from these parameters. So this is an image from the histogram simulator, and this is the source for how the histograms are generated in telemetry for linear and histogram and categorical histograms. So because it's JavaScript, we can pull this out and we can generate UDFs. Here's an example of some test cases for the exponential bucketing UDF. And we are able to know that this is the right set of buckets because we have examples of data that's already using this bucketing scheme, and we can kind of just test it on our own. So we have this nice way of generating buckets based on parameters that we get from metadata. And this is done for all the telemetry histograms, and it's also done for the functional bucketing in Glean. So there's this nice framework for embedding metadata so that we can generate buckets. Next, I'll talk about handling complex SQL. Complex can be complex. There's too much text for this query complex, and there's too much data for us to process complex. And I'll talk a little bit about both. So first is there's just too much text. So there is a limit on the number of SQL operations that BigQuery will handle. And the limit on the amount of text that BigQuery will parse is approximately 1 megabyte. And if you just take a look at the main ping schema for all the probes and whatnot, and how it's defined as JSON, it's 2.7 megabytes. So if we try to process all of the probes in one SQL query, we would just run into the complexity limit. And that was the case. And so we split up the GLAM SQL into two parts, scalars and histograms, not only because it makes sense logically to process the data in those two parts, but also because the query is just too big. We do the same type of thing for other queries. So the biggest example is the main summary query that was ported over from Spark over into BigQuery ETL. And the main summary query is actually done in two parts because of this complexity limit. So this is one way that we have to handle complexity in BigQuery ETL. The other is there's just too much data. So in this case, we have to reduce the size of large intermediate shuffles. So if you're familiar with Spark, or if you're not familiar with Spark, in order to do very large computations on very large data sets, you need to have a way to move data between different workers in a distributed system. And those shuffles cost a lot. So as of 2 days ago, these are our two main data sets that we're using for computing the GLAM data sets. The first is the client scalar aggregates data set, which is 1 row per metric, or 1 row per client, and it has a bunch of nested metrics. We have 817 million rows, and we have 48 terabytes of data. And this is over the last 3 versions. For the histogram aggregates, we have 818 million rows and 175 terabytes of data. So this is not an insignificant amount of data. If you're thinking about BigQuery, the market price of a scan of 1 terabyte of data is $5. So you can use that as a rough estimate for how expensive it is to compute aggregates across our entire population. So we have these gigantic data sets, and we want to build a data cube over the populations over time. And a data cube is basically a gigantic group by count. And we want to compute aggregates over permutations of our operating system versions, build IDs, and channel. And we also want to have more granular knobs on this. So we might want to say, like, we want aggregates for Windows release 84. But we might also want to say, we want to see the aggregates for all operating systems on release on version 84. So we have to do several layers of aggregates over the population. And so each client is represented multiple times in this very big group by statement. And so 800 million rows times however many different combinations causes BigQuery to go out of memory, which is kind of a strange sight to see, but it happens. Kind of not a great thing to see when you're trying to run the service for the long term. So this is how we solve large intermediate shuffles. Again, if you're familiar with Spark, the same kinds of tricks apply. So first, we use stratified sampling. We don't need all the data for release. We only need a small percentage of it. And so we use a 10% sample on release, and we weight the normalized histograms appropriately. So if we take a 10% sample to get 100%, we just multiply the aggregates by 10. And we don't need a sample from nightly or beta because it's a reasonably sized population. Next, we materialize intermediate results. Because there's all this intermediate state in the queries and they're really complex, what we can do is we can materialize some of those intermediate results so that the query is less complex and BigQuery doesn't have to handle keeping everything in memory. You can think of BigQuery as this data center size Spark cluster, but it doesn't mean that memory is infinite. So we can help BigQuery by just persisting things to disk. And this is one of the reasons why we materialize views when pulling out into systems like Spark. When we're materializing intermediate results too, we can do a thing where we run queries over samples of the data. So we're not processing all the data at once. And so this is another technique that we can use to make sure that the query is complete in a reasonable amount of compute. And so the final thing is that we want to limit the number of scans when cubing. So when we were originally building out the queries, we did this. We did multiple group by statements where we would union the results together. But doing this meant that we had to read and scan over the source data multiple times. And one way of reducing the number of scans is to cross-join on a small set of dimensions. So you can imagine you have a small set of static dimensions that you want to compute over. So you have operating system and null, and you create the set of rows that you want to build first, and then you compute a group by, which is an interesting way of reducing the amount of data you're scanning. So lots of tricks to handle this big problem of there's just too much data to compute aggregates. So now I'll talk about some of the challenges that came with implementing GLAM for Android, for Firefox for Android, or more specifically, generalizing this to Gleam. And so this came into two parts. First is templating the queries so that they're more generic, and then revisiting some assumptions that we had about Firefox releases. So in general, we just templated all the queries. So we went from desktop, we ported over the scripts so that they could be run with Gleam. And Gleam is really nice because they're split up into multiple pings. So we no longer have to split into the scalar and histogram views because we have to. We do it because it's a nice logical split. But it requires us to be able to run the same query on the baseline ping, the metrics ping, and any other ping that comes with Gleam. So we have one script that generates a query for each of these, and then we build a view on top of this that we can use for the rest of the pipeline. And so in the BigQuery ETL repository, we've introduced Jinja. And Jinja is a templating engine that you might be familiar with if you've ever done Flask programming, for example. It's also the thing that powers Airflow templates. But this is a nice framework for us to embed information into queries and template these things. On the right-hand side, you can see a directed acyclic graph of the queries for testing. So this is the DAG that was generated from building all the tests necessary for GLAM. And so if you remember from Marina's slides, the directed acyclic graph, you can see how this is a little different. On this left-hand side, there's this gigantic list of different pings, and these are from 3 different products and all of their pings. So there's just a lot of queries. I think there's probably almost 100 different queries that we have to organize to do the GLAM ETL process. And next, we have to revisit some of the assumptions we had about Firefox releases. And this is kind of a complicating factor for adding Phoenix to GLAM. So on Gleam, the meaning of a channel is different. And on Android, the way that we do releases is different because there's a different application for each channel, nightly, beta, and release. They're all separate applications. So Phoenix actually had 3 separate applications, and the meaning of these applications changed over time when we did the migration from Fennec to Phoenix. So what used to be org Mozilla Phoenix, when it was originally nightly, I think, it's now release. And so the populations have changed over time. And this is a complicating factor for doing our aggregates. Additionally, we found out that the nightly and beta channels aren't using semantic versioning for their application version. So they're using some sort of like nightly plus a timestamp for their versions, where we expect something like 84.0.A1. And so to kind of get around all these different business exceptions, we built a shim layer that provides a logical application ID for GLAM. And we can do things like looking at the Gecko view version in the metrics ping to estimate what the version should be for a particular ping. So this was probably the most difficult part of adding Phoenix to GLAM, which is just dealing with all of the Firefox for Android isms. And so in summary, to handle all the challenges of aggregating data in GLAM, we use dynamic queries to keep the aggregates up to date with information from an upstream source of truth. And we can use metadata from the source of truth to parameterize our queries and to aggregate our data in various different ways. There are challenges in the complexity of SQL in the BigQuery ETL repository. And so there are various different ways to handle that complex SQL, either to break it up into multiple queries or to be clever about the use of data. And finally, the ETL for Firefox or Android required generalizing the desktop queries and revisiting some of our assumptions about how that data is to be aggregated. So thank you. Questions or comments?